So, as usual, my name is Ikechukwu, and we'll be having our physics lecture or physics night class. This is week 6, and I'm happy to have all of you here. So, now let's start. Um, since the topic for today is talking about work, energy, and power, it would be wise to start from the definition of work. Most of us have heard that work is, we've heard from different sources, probably from teachings in school or from friends or from even our notes. We've seen that they defined work as the product of force times distance. So from what I have here, I said work is a fundamental concept in physics that tries to describe the transfer of energy. It is said to be done when a force causes displacement in the direction of force. So what am I saying? Work done is truly the product of force times distance, because you cannot mention anything about, you cannot talk about work done when there is no force, and you cannot say there is work done when no distance was covered or when there was no change in position, if I would call it that way. And as we should know, work done is a vector quantity, so it has magnitude and also direction. So as you are trying to measure work done, there would always be the direction when you're talking about work done. So either the object or whatsoever the work is being done vertically upwards, left, or just there has to be sorry, there has to be a direction which which corresponds to the change in position or displacement. So that's the reason why you are saying from this definition I said it is done when force causes displacement. So when force causes displacement is the change in position with respect to a direction. So we have here, for example, when you lift an object, you are applying force to move it upwards. So as I was mentioning earlier, I said you cannot say you are carrying out work without a change in position and also in a particular direction. So work has to do with force. You have to consume, you have to burn some kind of, you have to use an amount of force in a particular direction to cause change in distance of any of the object that the force is being applied on. So the transfer of energy from your muscles to the object is considered as work. So now we're talking about the work done when you're trying to pull up an object or lift an object from a table. So this lesson might not be long because of the way the structure of the topic is not really bulky like that. So for this week, this is what we will be treating. So similar to lifting your box or lifting whatsoever, there's always pull and push. There's always pull and push. Push is when you're trying to apply force. We are talking about human direction now. You're trying to apply force on a particular thing to where the force is going to be going, like away from the user, then pull from the applied force. I mean, so when you're talking about pull is when the object you are trying to apply force on is coming towards the user. So that's pulling motion. So the formula for work done is force times distance. Generally, they see it as force times distance, but in real sense, it's not just force times distance. It is force times distance times cos theta. So the reason why the formula becomes force times distance is when there is no angle to which the direction of force is being applied. So when there is an angle, the formula will be taking its full shape, which is force times distance times cos theta. So cos theta is the angle that the force makes with the horizontal. Cos theta is that angle that the applied force makes with the horizontal. So work done is always the product of force times distance times the cos of the angle between the direction of force and the horizontal. So when there is no angle, cos theta will give us 0. Sorry, will give us 1. When there is no angle, the angle will mean that the angle is 0. So cos theta is 1. And if you multiply it by the formula, you'll be having work is equals to force times distance. So that's the reason why you see some of the times you write the formula as work done equals to force times distance. So they assume that the direction, there was no angle between the force and
So I
the
can't hear you
direction
any
on the
longer.
horizontal. Sorry.
I can't hear you.
Can everybody hear me? Can you
Yes,
guys
I
hear
can
me?
hear
Yes,
you
I can
clearly.
hear you.
Yes, I can hear you clearly.
Okay, okay. I don't know. Probably your network is lagging. I don't know. Maybe you could disconnect and try reconnecting again. Because I think I'm trying to be audible and other persons are hearing what I'm saying. So just try seeing whether you could log off and come in again. So, and sorry about that. So, as we were saying, work is the product of force times distance times the cos of the angle towards the applied force and the horizontal, between the applied force and the horizontal. So, let's move on to our next slide. So, we'll move further in this topic. So, I said there are examples of work. We can see lifting, pushing,
Sir, please, I want
and
to like
pulling.
hack the other thing. I want to screenshot it.
Okay, can you see it now?
I can see it now. Thank you.
Okay, so that's
I've
this
done it,
one.
please. You can move to the
Then,
next slide.
okay, so let's go on to the next slide. The next slide, we have example of work. So we have lifting, pushing, and pulling. Lifting, pushing, and pulling. So these might not be the only forms or examples of work, but basically, I'm just mentioning usually in this physics, in the course of this of your elementary level physics, you'll be seeing just these expressions of work where you'll be seeing lifting, pulling, pushing, especially at this level. You'll be seeing these as the types of questions you'll be experiencing in work or when you're talking about work done. So you could hear it as work, or you could also hear it as work done. There is no difference. Work is the same as work done. So before I move on to the next slide, there is this important there is this important okay, there's an important there's an important idea I would need you people to know. The formula for um work done, it actually is work W equals to F times D times cos theta. But in some cases, you see it as W equals to minus F times D times cos theta. Minus F times D times cos theta. So in those cases are like um the basic forms of the expression for work done, the basic form of the formula. This kind of work done, the formula for this work done formula that is W equals F times D is called work done, mechanical work done. Mechanical work done. So there is the work done. You can see the formula for work done to be in some other cases to be pressure times volume. In some other cases, it can be pressure times volume. In some cases, you will see it as force times distance, depending on the system that the work is being done on. So for this level, you will just be seeing it as force times distance times cos of the angle. I'm mentioning this because of persons that maybe they might go forward in the study of physics or maybe engineering or stuff like that. So when you see work done, there are different types of work done. They have mechanical work done, electrical work done. We also have thermal work done. There are different forms of work. There are different forms of work. So this is the basic form for mechanical work done. And some places you might see it as minus F times D times cos theta. So the minus sign does not actually mean that it is changing the formula. It's just trying to show whether the work is done on the system or by the system. This one is not really your level. I'm just mentioning this just in case you might see something like that. You will not think that there's an error in the formula. Some cases you might see that work done is equal to minus FD cos theta. But for this level, just take it as work done equals force times distance times cos theta. So let's move on to um, energy. So the topic was under the topic we are treating is work, energy, and power.
Hello, sir.
So energy. Yeah, I can hear you.
Hello, sir.
Yeah, I
Yeah.
can hear you.
Uh-huh. My question is on the formula.
Okay.
You said that sometimes you can see positive or negative sign.
Yes.
There's something you explained there. When it's negative sign, is it work done by or work done in? I don't know how you explained it.
Okay. For the sake of this level of study, I would like not to complicate it because when if I start bringing that stuff in here, it might start making things complicated. when you say work is done by the system or work is done on the system. But for the scope of this lesson and for your exam sake, just the formula for simplicity is just force times distance, force times distance, then times cos theta. So I don't want to go into bring in that aspect such that it will not start confusing some other persons, because sometimes too much information can make
But
things
I've
get
seen
a little
such.
bit
I've
confusing.
seen a quest. I've seen a question concerning that somewhere. I don't know the
In
year.
JUPEB,
Uh,
in JUPEB. Okay.
yes.
In case you see that kind of question, when you hear that work is done by the system, in that case, the work done is usually positive. The total work done, sorry, the total work done is going to be negative when the work is done by the system. But when the work is done on the system, the work done would be positive. And the reason why that is so is because usually this kind of formula is used when you're trying to think about work done by maybe a gaseous system or piston and ring kind of system, where you see the formula for work done would be work equals to maybe minus P delta V, or minus P V1, maybe V2 minus V1. So in that case, when you then have work done by the system, when the system is one that is doing work on the environment, it will mean that the system's initial volume would be lower than its final volume. So when the work is done by the system, the final answer is usually negative. When the work is done on the system, the final answer is usually positive. Okay, so in case you see maybe a question that asks you what is the value for the work done when the work is done on the system or by the system. When the work is done by the system, the value for work done is negative. So if you're writing, just write when work is done by the system, the value for work is negative. And when work is done on the system, the value for work is positive. That is the mathematical value is positive. I don't know whether I've cleared that answer.
Yes. Thank you, sir.
Just
Yes, sir, you have.
so that was just Yeah, thank you. So let's focus on energy. So we've treated work. The topic is work, energy, and power. So we are now on energy. And I remember in one of our first lessons, I guess week 1 or week 2, we were talking about the different forms of energy. And I mentioned thermal energy, radiant energy, light energy, chemical energy, nuclear, electrical, gravitational, and mechanical energy. So these energies, they can be transformed from one form to another. We'll be seeing that in another slide. But these are the basic or the most common forms of energy. Thermal energy, the one that is gotten from heat. Radiant energy, the one that is gotten from the sun, that's the sun's radiation. The light energy, the one that is gotten from as a result of white light or light, spectrums of light, not radiation, not the one from the sun. Because sun too is a form of light energy, but they call it specifically radiant energy. So light energy is the one that is gotten from a particular band of the electromagnetic spectrum. Then we have chemical energy. Chemical energy is the one that is generated from chemical reactions. Chemical reactions, maybe electrolysis reaction or battery, or these your galvanic cell reactions. The energy that is generated from that kind of system is called chemical energy. And nuclear energy, the kind of energy that is generated when you have stuff like radioactive decay, or you have nuclear fission or nuclear fusion. Those are the energy that are generated, then they are called nuclear energy. So we also have electrical energy, the one that occurs as a result of the movement of charged species in a particular system. So once they move around, they generate a kind of energy. The same thing with gravitational energy. As you can remember, if you can remember when I was talking in one of the classes, I said when an object's size is big enough and very big, so that it can bend time and space, it generates a kind of gravitational pull around itself. And that pull is kind of like a form of energy to pull things towards itself. So that's gravitational energy. Then we also have mechanical energy, the one that happens when we apply force, manual force. So these are the kinds of energy. Then we can also see it as kinetic energy. Kinetic energy, that's the energy that an object has as a result of its position in motion. Kinetic energy is the kind of energy that an object has as a result of its position being in motion. Potential energy is the one that a particular object has as a result of its position being static. When an object is static, there's an amount of energy that it generates or that it possesses And that kind of energy is called potential energy, because the energy is the energy when the object is not moving. There might still be some other energy where you some other kinds of energy like let me see, I think just flashed my mind. Yeah, internal energy, the energy of a system naturally, every system naturally. So there are different forms of energy, but basically for elementary level, you hear just stuff like potential, kinetic, mechanical, chemical, electrical, all these ones we are seeing here. So let's move on to our next slide. Potential energy. I was trying to I explained potential energy as I was explaining, but I did not know you guys are not hearing me. So potential energy is the energy that a body possesses as a result of its position being static. That is, for its position being static, as an object is not in motion, the energy that the object acquires because it is not in motion, or the energy that the object possesses because it is not in motion, is called potential energy. Is the energy an object possesses as a result of it not being in motion. So that's potential energy. So an example of that kind of energy is okay, not really sure. So potential energy is that energy that an energy possesses as a result of it not being in motion. So I mentioned I was trying to say something about the unit for work done. I said the unit for work done is joules. Work done is measured in joules or kilogram meter squared per second squared. Is measured in joules or kilogram meter squares per second squared. Can you guys hear me?
Yes, I can hear you.
No,
Yes.
sir, sir, what did you say?
Okay,
Said
I
that the
said
unit of work.
the unit for work done for work is joules or kilogram meter squared per second squared. Kilogram meter squared per second squared. So the unit for work is joules. The same thing applies to the unit of energy. The unit of energy is also joules and also kilogram meters squared per second square. So now, going on to power. Power is I was saying earlier before I got disconnected. I did not know I was disconnected. Power is the simplest definition. It is the work done per time. That's what power is. The simplest definition for power is simply like it is the work done per time. But from what I have here, I say it is the rate at which work is done. So power is a measure of work done per time. So if someone works for probably 3 hours, the kind of energy that was expended within that time is going to be called the power that the person imputes. The energy the person expends per time is called the power that the person consumed in that process. It's known as the power that the person consumed in that process. So when you talk about power, you cannot talk about power without comparing the work done to a particular time frame. So it is usually given with the formula power equals work done over time. So as I said, the simplest definition is that it is the work done per time. So the unit for power is watt or joules per second. Is watt or joules per second. The unit for power is watt, W-A-T-T, or capital letter W, watt or joules per second. Watts or joules per second, or kilogram meter square per second cube. Kilogram meter square per second cube. So that's the measure, that's the unit for measuring power. So let's move on to our next slide. So here we have units for measurement. Okay, I even have it here. We have units for measurement, and we have that work and energy. They are measured in joules, as I said initially. We also have that power is measured in watts as W, and the large scale energy, that's like a form of checking the amount of energy consumed at a particular period of time, is known as kilowatts per hour. Is measured in kilowatt hour. So this is the kind of measurement that they use in electricity consumption. So power consumption is usually measured in this kind of, usually measured like this. Power consumption usually measured in watts per hour or kilowatts per hour, usually in kilowatts per hour. So that being said, let's move on to our relationship between energy and power. As I said initially at the beginning of this lesson would not necessarily, does not would not be
Sir,
that bulky.
please, can you go back to
It will not be that bulky.
the other slide? Please, I'm trying to screenshot it.
Okay, okay. So here you go. So now we have energy, the relationship between energy and power. So we know already now that power
Back to the
is
movie.
the measure of. We've learned that power is measure of energy consumed per time or work done consumed per time. So the amount of energy transferred per time is known as power. The formula is energy over time or work done over time. You know, I said the formula, the units for work done and energy, they are the same. So in some cases, you might see it as power being equal to energy per time or power being equal to work done per time. So your idea should just be that work done is a form of energy also. Work is a form of energy also. So what this means is just that when you are asked to calculate the power, they are only trying to ask you to check the amount of energy that was consumed within a particular time frame. And typical questions under power will be, they will tell you calculate the power of in a particular system, or the power possessed by a system which carried out a work of, they will give you a particular work, and over a period of maybe a particular period of time. So it's very, very simple. Usually questions on under power are usually very simple. So the power here we're talking about is mechanical power. As I said from the beginning, work we're talking about is mechanical work. So when you go to electricity, the formula for power is going to be different. The formula for power is going to be different. In that case, you'll be seeing something like IV, power equals to IV or I squared R. So for the case we are dealing with, it is the formula for power we are dealing with here is energy over time or work done over time. So power and energy, they are similar, just that power is the rate at which energy is being consumed. Power and energy, they are similar, just that power is the rate at which energy is being consumed. So that's the relationship between both of them. They are both similar and their units are similar, but just that one of them has is the same but per time. The same thing with, so assuming you had an energy consumed to be 1,000, the general energy consumed by a system is 1,000. If you have to check the power, you need to then check how long the energy or that system carried out work, or how long that system expended that energy. So when you start putting into consideration time, you're no longer talking about energy, you're talking about power. So now let's move on to conversion between units. Conversion between units. So power, when you see power, if this one, I'll need to mention it out. I'll need to state it out. When you see power, the formula for power, you usually see it in kilowatts. You usually see it in kilowatts. Most of the times you will see it in kilowatts, and it is common for people to think that they should just use the formula like that. So they said, okay, calculate the power consumed by the power used by a particular system that had an energy of maybe 300. Okay, you know what? Let me just give a question before I go on. Let me give a question. Everybody, take out your pen and paper and let's solve this question. Take out the pen and paper. Let's solve this question. Are we ready? Hello.
Yes, yes, sir. We are ready.
Yes, sir.
I'm ready.
Hello. Can you guys hear me?
Yes,
Okay.
sir.
Okay. Yeah. Thank God. I thought
Sorry,
I
sorry,
was
sir.
connected already. So everybody, get out your piece. Yeah. Get out a piece of paper and let me give a quick question. It's not going to be difficult. It's just basic question, but I think I will need to bring out the question so that what I'm trying to say next will become clear. So the question is,
Yes, sir.
if
But that difference you mentioned between power and energy, to me, it's not clear. Oh.
yeah, okay, the difference is just simple. Power is the energy consumed per time or the energy received per time. Energy can either be received, that is, can be either gained or lost. So the power is the energy gain or energy loss per time. So that's just what power, that's just the difference. When you start measuring time with power, or start measuring the energy consumed per time, you're no longer talking about just energy. You're not talking about power. So the difference between them is one of them is just talking about it as a particular entity, energy as a particular entity, work done as a particular entity, as an amount of something. So when you start talking about the amount of that thing at a particular given period of time, or the amount of how the energy was dissipated over a period of time, you're talking about power. That's when you start mentioning the particular and the energy with respect to time. You're no longer talking about energy, you're talking about power. I don't know whether it's clear now. I don't know, is it clear now? Hello?
I can, sir,
No,
please,
sir,
you are
please, can you?
fast.
You were very fast, I swear.
You are too fast.
Okay, sorry. I said when you start talking about power, when the difference between power and energy is that energy is just an amount of is an amount. It's talking about like the amount of a particular entity, the amount of maybe work, the amount of energy is like an amount, a quantity. Energy is a quantity, work done is quantity. But now when you're talking about power, now you're not just talking about the quantity of that particular thing now. You're talking about the quantity that is being used up at a period of time, or the quantity of that thing that is being created over a period of time. So when you start bringing it, you are then talking about power. But when you're not talking about the period of time, you're just talking about the quantity of energy, or the quantity of the quantity of energy. You're talking about work done. When you're talking about just the energy, the amount of energy, you're talking about basically the regular energy we know. But when you start mentioning it with respect to a particular time frame, you're then talking about power. I don't know whether it's clear now.
Yes, it's very clear to me.
Yes, sir. It's clear.
Yes, yes, sir.
Okay.
Thank
Okay.
It's clear. Thank
So
you,
now
sir.
let's move on to the example I was trying to give. I said I have a quick question for everyone. So on your piece of paper, let's just, in case you can even do it offhand, but just let's be cautious. So now let's calculate. If the question now, and I'm calling out the question, if a particular system had a had a power of, if a particular system had the power of 10,000 kilowatts, if a particular system, as if a particular system consume a power of 10,000 kW for 100 seconds.
Sir, please don't be
For
angry.
100
Please
seconds.
don't be angry. Like, can you repeat it? Because my network went out, so I could not hear what you were saying again.
Okay. If a system consume the power of 10,000 kilowatts, if a system consume the power of 10,000 kW, if a system consume a power of 10,000 kW for 100 seconds, for 100 seconds, what was the amount of energy consumed? What was the amount of energy consumed? What was the amount of energy consumed? So if you have your answer, just turn on your mic and tell me your answer. Let's see, because there's an idea I want to bring out.
Hello, sir, I was cut off. Oh. What was the amount? That's where I heard last.
Okay, what was the amount of energy consumed? So if you have your answer, I would like you to just give your answer.
Energy is 1 times 10 raised power 9 joules.
1 times 10 raised power 9 joules. Okay. Who else has another answer?
I have 1 times 10 raised to power 6 joules.
Okay, 1 times 10 raised power 6 joules. Who else has another answer? Who else has another answer?
Please don't be angry. I didn't get the question. My network went out again. I'm in school and we have a network in my school. So I cannot
Okay.
like stop this. I don't know what
We are,
you said.
we are trying to find the energy consumed if when the power we are trying the question was calculate the if power of 10,000 kilowatts was consumed for 100 seconds. Power 10,000 kilowatts. Power of 10,000 kilowatts was consumed for a period of 100 seconds. What is the amount of energy spent or amount of energy consumed? So that's the question.
Thank you, sir. Thank you.
You're welcome. So let me just give 2 more minutes for anybody to confirm the answer. And people that are just coming in, that people will be having lags to solve their own. Okay, so who else has another answer? There was 1 times 10 to the power of 9, and there was another person that said 1 times 10 to the power of 6. So who has an answer to either support the answers or reject the answers? Okay, because of the sake of time, for the sake of time, I'll just have to go to the final answer. So the final answer is actually 1 times 10 to the power of 9, not 1 times 10 to the power of 6. And this was the reason why I brought up this question. The question stated that power of 10,000 kilowatts. So mostly they will give you power in kilowatts. So that they give you power in kilowatts does not mean you should use the kilowatt direct. You're not supposed to use the kilowatt direct. You need to convert from kilowatt to watts because kilowatt is 1,000 watts. So 1,000 watts make 1 kilowatt. So when they give you kilowatt, don't be deceived to just use it straight up. Power normally everybody know that they measure power in kilowatt. But when you are trying to solve, don't be deceived to use it straight as kilowatts. Instead, convert it from kilowatts to watts by multiplying it by 1,000. So by multiplying by 1,000, if you multiply by 1,000, you'll be getting your final answer to be 1 times 10 to the power of 9. So I just hope that that's clear.
Yes, sir.
No, sir, it's not. Please, I don't know if you can tell me the formula which used to like do it.
Power is equal to energy over time. Power is equal to energy over time. So when we have power of 10,000 kilowatts, it's same as saying how you have power of
Okay, sir. Okay, sir.
10,000 times 1,000. Yeah, all over. So it equals to energy over 1,000. So when you do the math, you'll be having 1 billion as your quantity of energy consumed. That is something as 1 times 10 to the power of 9. So that's what this conversion between power is. This portion was structured out for. To know that when you see the unit for power, don't be deceived to know that to just use the power directly. Observe whether they gave you power as kilowatts or kilowatt hour. If you are given as kilowatt hour, just know that you either convert your previous time to hour, that's the other time that they gave you to hour, so that you'll be on the same level, or you convert from kilowatt hour to kilowatt second. Convert from kilowatt hour to kilowatt second. And to convert from kilowatt hour to kilowatt second, it's multiplied by 3,600. So convert from kilowatt hour to kilowatt second, you multiply by 3,600. So to convert from kilowatt to watt now, you'll be multiplying by 1,000. So now converting straight from kilowatt hour to watt second would then be 1,000 times 3,600. That's all we have on this my screen here at the top here. Converting from kilowatt hour to watt second. So take note, this portion I especially carved it out because of it's a major mistake that can happen in most exam cases. Majorly, probably many of us even try questions, past questions on power, and we see questions on power. Most likely, would make this mistake of using kilowatt directly, except we probably are now aware of it now. So whenever you see a question on power, be very sure that you are not using the kilowatt, and if you are using hour at all in any point, make sure that if you, anywhere, any unit for second, any unit for time should always be constant throughout. So preferably, whenever you're giving power, convert it from kilowatt or kilowatt hour to watt or watt second. So converting from kilowatt to watt is by multiplying it by 1,000. Converting from kilowatt hour to watt second is multiplied by 1,000 times 3,600. I don't know if everybody is on the same page now.
Yes, sir. So, sir, please, your answer was what? Don't be angry. Like, what was your answer for the thing that you asked?
1 billion, 1 billion, 1 billion, or 1 times 10 to the power of 9.
Okay, sir, thanks.
1
So wait,
billion.
don't be angry. So if you times
Yeah.
10,000 times 1,000 will give you 1 billion. So then I really get like then you now divide it by 100. That's the time in seconds. See?
No, you will not divide, you multiply by 100. You multiply by 100. You will not divide, you multiply by, because the formula is power equals watt over time, which equals energy over time. So it's going to be like P is equal to E over T. So we've already gotten our P to be 10,000 times 100. So 10,000 times 1,000. So then to make energy
We'll
is always a
give you
formula you
1 billion.
multiply.
Then
Yes,
you now get
yes,
1
1
billion
billion. That
times
will
100.
be no, no, no,
Okay,
no.
thank you,
It
sir.
give you 10 million. It give you 10 million. 10 million.
Okay,
Yeah,
okay.
10 million. Then multiplied by
Thank
100 by 100. No,
by the time. Okay, sir, thank you.
yeah,
Hello, sir. Hello, sir.
yeah. I'm listening. Yeah,
The
I'm listening.
example you gave above, 1 kilowatt hour is equals to
Yeah,
1,000 watt times 360 seconds. Is it the 1 hour that is 360 seconds?
3,600 seconds. Yes,
3,600 seconds.
yes, yes.
1 hour.
That is 60 times 60. 1
60
hour
times
is 60 minutes. Yeah, 60 minutes in times 60 seconds. So that's also give you the 3,600.
Okay, you first change to minutes and then you change to
Yes,
seconds.
yes.
Okay. Thank you.
Excuse me, sir. This
So we are good to
conversion
go here now.
from power. Excuse me, sir. Sir,
Yeah, conversion from, yeah, I can hear you.
excuse me, sir. Please, I have a question. Okay, sir. I said
Yeah,
this
go on.
conversion from that is in respect to the question you